In this video, I'd like to discuss what vectors are, and I'd like to discuss different ways of representing specific vectors. We'll be talking about terms like components and lengths of vectors. All right. So first of all, let's go ahead and define what a vector is. A vector is simply a group of a set of numbers. All right. Now that's a nice simple definition that shouldn't confuse anybody. Now why do we need vectors? Why were they invented? Well, sometimes we need more than one number. All right. If you wanted to specify a phone number, clearly you need more than one number, or a social security card, your social security number. If you wanted to specify the position on a line, you only need one number. However, what about if you wanted to specify the position on an XY plane? All right, in that case, you would need two numbers. Okay, so you would probably not be surprised if I told you that this green dot, that position was 1, 2. Okay, so we usually refer to those as coordinates, but notice that using my definition, can you see that that's also a vector? Okay, so coordinates are a vector. Also, your phone number is a vector. All right, your social security number is a vector. Now, vectors are used all over the place anytime you need more than one number. Okay, even in painting you use vectors. Let me explain how. You may know that you could make every color from 3 basic primary colors. All right, I believe it's yellow, blue, and people talk about RGB, red, green, blue, where they really mean a specific shade of blue, cyan, I think. But the point is, we have RGB monitors. Okay, you can define all colors in terms of those 3. So let's say that I had a color. I wanted to paint my wall in my house. So the color I'm thinking of, let's say, is 22% red, 31% green. All right, and then 47% of the liquid, the paint I have to mix together, is blue, and that's how I make my color. So can you see that I can specify my color as 3 numbers, 0.22? So I bet you didn't think that even in painting you use vectors. Okay, so this vector right here represents my color. All right, so that's yet another example. Okay, so vectors are very useful. That's why we invented them and why we have a special math we're going to learn later. All right. Now, another obvious example of a vector besides coordinates define position. So now position can be a vector. It is a vector if you're talking about if you go beyond the line. Okay. You can also define velocity. Velocity is a vector if you're talking about more than one direction. Okay, so I started out by giving you how fast something is moving along the line, and I gave you this formula. All right, what if, and I called that v. Now let's call this v sub x for right now. Okay, what if I had something that was moving in not the direction of the x-axis, but what if it was moving at a little bit more interesting direction? Like what if something was moving, let's say, in the direction of this red arrow? All right, so in that case it's still moving horizontally, but it's also moving vertically. All right, so we could define, we've already defined the ratio delta x over delta t. We could make up a new ratio of how fast the y value is changing with time. Okay, and those two ratios together would make a new vector. You see that? You collect the ratios and we call that the velocity vector. Okay. We also could decide, we could, if there was, let's say the red arrow was a certain movement, the x value changed by a certain amount, the y value changed by a certain amount, we could package those together, and that would be the displacement vector. All right. All right, so that's all well and good. We can define vectors this way, and you'll see later how useful they are. Let me now talk about components. So what do I mean by that? All right, so even though vectors are sets of numbers, it is often useful to work with pictures that represent vectors. All right, so we all love pictures. Some people's minds work best with pictures. The reason we learn algebra is sometimes working with equations, expressions is useful, but we also learn plotting, plot functions, quadratic expressions, things like that, because sometimes pictures are useful, give more information or different information. Okay. Likewise, you can think of there's a picture way to think of vectors. All right, and if you understand coordinates, you already understand this. All right, let's go back to let's give an example of a vector 3, 4. Okay, now we can interpret that. We can make an arrow out of that. Excuse me, by draw an XY plane. Okay, and imagine drawing an arrow from the origin to the coordinate represented by that vector. So that would be the green dot right there is the point, the coordinates 3, 4. All right, so I start from the origin and I draw a vector at that point. Okay, so this arrow, okay, this arrow represents or corresponds to the vector 3, 4. Okay? Now, when you do this, you can ask yourself this question. All right, so we have this arrow pointing in some direction, and what would be the length of, let's say, the shadow underneath it if the sun was right above? What is the length of this guy right there? Okay, and we could also say what is the height of the point, the top of the arrow. If you ask that question, you would be asking for that stick. All right, so those are the two lengths that make up the vector components. Okay, so let me label that on my picture. So these are the vector components. They are let's say let me define it down here. So vector components are line segments that, or actually, you know what, not even line segments. Let me be more careful. So you can think of these as vectors as well. I could put arrowheads right there. So the black arrow is, that's associated with these two orange arrows that make a right angle the way they did. Okay, so vector components are vectors. They themselves are vectors. Vectors associated with a given vector. All right, in some way. All right, and we could say that vector components make right triangles with the given vector as the hypotenuse. Alright, so you can see there the black vector, the original vector, is the hypotenuse of a right triangle formed from the orange vectors, or with the orange vectors, and the right angle would be what I just labeled with the little right angle box. Okay, so you could ask yourself, what are the lengths of the vector components? Okay, the vector component lying along the x-axis clearly has a length of 3. The vector component, vertical vector component, clearly has a length of 4. Okay, let's do some other examples. Let's say that I had a vector 1, 3. Let's see what, and then let's do 2 of them. Let's do -2, -1, because you could have negative numbers when you're talking about vectors as well. So I'm going to draw the arrow, and then I'm going to ask for the components. All right. So we'll draw an x-axis and a y-axis. Can you, before I do this, could you pause the video and guess what I'm going to draw here in a few seconds? Where would the arrows be pointing? And let me give a name to these two vectors. I haven't talked about this yet, but you could, in addition to talking about the group of numbers, you can give a name, like we can call the first one A, the A vector, but to make it clear that we're talking about a vector, we'll put an arrow on top, since arrows remind people of vectors. And maybe the next one we could call that the B vector, and so I'll have to put an arrow above that one. Alright, so what I want you to do is I want you to draw the arrow for the A vector and the B vector before I do. Alright, so here I go. I will now draw it. So the A vector starts from the origin to the point 1, 3. So it's going to look something like this. And the B vector starts from the origin and goes to the point -2, -1. So that's going to look something like that. So let me label those. This is the A vector and this is the B vector. Okay. Then I can make a right triangle to find the components. In this case, I want the horizontal and vertical components. All right. And let me show you something that you might be concerned about, and you'll see that it really doesn't matter. I talked about making a right triangle to get the components, right? For the vector A, if I choose this blue triangle, the horizontal and vertical sticks have the same exact length as if I had chosen this green right triangle instead. Okay, check that for yourself, so you'll see it doesn't really matter which of those you select. Okay, and that's a good thing, so that it's just one less thing to worry about. And then likewise for the B vector, you can select the right triangle with these green sides, or you can select the right triangle with these blue sides. Okay, they have the same vertical and horizontal sticks, vectors. All right, so the A, that vector is composed of sides of length 1 and, well, let me change colors here. Composed of lengths 1 and sticks of lengths 1 and 3. The B vector is composed of sticks of lengths 2 and 1. All right. Notice that you could get the lengths of the components simply by the way that I wrote the vector the first time. So I had 1, 3. So you immediately know the lengths of the components. Same, even if they're negative, you just take the absolute value. Okay. Now, when we talk, if I say lengths of components, I want positive numbers. But if I just say I want the components, what that usually implies is they want the numbers. Okay. The numbers that are the numbers that make up the vector. All right. So for vector A, I'd say the components are 1 and 3, and then for B, I'd say the components are -2 and -1. Okay. Now, let's continue. Now that we know what components are, let's build on what we've got. All right. So suppose that I had a vector, and suppose that I had drawn the components of the vector with some right triangle. All right, and suppose that I also knew that the length of the components of the vector were, let's say, 3 and 4. All right. However, what I asked you was, I said, you know what? I want to know what the length of the blue vector is, the original vector. All right. Well, we haven't talked about the length of an arrow, although you could probably guess how to do it. Okay, if you had a right triangle and you knew the lengths of the components, the other sides of the right triangle, you could simply use the Pythagorean theorem. Okay, so the square root of 3 squared plus 4 squared would give you the length of the vector. So in this case, we would say that the length of the vector, quote unquote, length. And now I said that a vector was a set of numbers. Now a bunch of numbers between parentheses have no length. Okay, so when people say the length of a vector, they are immediately asking, they're implying they want you to switch your thinking to the arrow picture. Okay, so they really mean the length of the arrow, the picture of the arrow that corresponds to the vector. Okay, so that's how we get that. All right, now another question that people will sometimes ask is, what is the direction of the vector? Now by that, of course, they mean the direction of the arrow associated with the vector. Okay, the one way to give the direction is, well, if you give the components, the components allow you to exactly specify the position of the tip of the arrow. So you would draw it from the origin to the components would specify the point where the head is. All right. Now another way to specify the direction is by giving this angle right there. And you could say, well, the arrow is this certain number of degrees or certain number of radians above the horizontal axis, right? Above the plus x direction ray or something like that. All right. Now you could get that angle from the components. All right. The tangent is a function that you can see on your calculator. If you were to type the tangent of any angle, you would get a number. Okay, and that number will equal a certain ratio. You can have fun with this and see that you'll always get the ratio of the two sides of a triangle. All right. So in this case, this angle is the ratio of 4 and 3. Okay. Now we're not interested in the tangent. We're interested in the angle itself. All right. In order to find the value, the number of degrees or the number of radians in the angle, you need to use a related button on your calculator. So what we would do is we would say the inverse tangent, it's sometimes called. So you press that button and you plug in the ratio. All right. Now let's do that all on our calculators, and let's make sure that we get the right answer. My guess, or the reason I'm doing this, is a lot of times people get confused between whether their calculator uses degrees or radians. All right, so let's make sure that you know what your calculator uses. All right, so the inverse tangent of 4 divided by 3, or 1.333, whatever you prefer. All right, and if you do that, you should get about 53 degrees, 53.1. All right, if you are in radian mode, then you probably got a number close to 1. Okay, so make sure you know when I ask for degrees or radians how to switch the mode of your calculator. Okay, very good. So now to summarize all of that, let's do this. So an example of a vector would be, and I'm going to use variables now to talk in generalities. So x comma y. Okay, the length of a vector x comma y is the square root of the sum, and now I'm going to have to switch to not typing to writing, so that would be the square root of the x squared plus y squared. So the square root of the sum x squared plus y squared. So in other words, the square root, putting it all together, x squared plus y squared. Okay, and then lastly, if I have a vector and I have, let's say, components x and y, so here's the length x squared plus y squared, and the angle is the inverse tangent of y over x. I prefer personally calling it the arctangent, but if you use the other way, everybody knows what you mean. Okay, and let me give you, so that summarizes what I've talked so far. Let me mention one other direction. This shows you how to go from the components to the length and the angle. What about if you wanted to go the other way? What if I had a vector and I told you that the length was L and the angle was theta, but I wanted to know what x and y were? Okay, y in that case is going to be L times sine of whatever that angle is. So sine is another function on your calculator that you could plug in. X is going to be L times cosine of an angle. Okay, let me do an example of that, and in the next video I'll talk more about these trig functions, sine, cosine, and tangent. So I'm just using them now to finish the vector video. Alright, so for example, if I had 30 degrees here, and let's say this length was 10, okay, so for the vertical length of that stick I would do 10 sine of 30, and then for the bottom length of that stick I would do 10 cosine of 30, and I just happen to know that if you punch that into your calculator you're going to get 5. Alright, and I just happen to know that the other one is going to be 5 times root 2. Okay, and so that completes everything I wanted to say for now about vectors.